I am talking about real-time edge cloud services and from an age of information perspective. And the kind of applications we're interested in include vehicular safety messaging and augmented reality. And these applications typically involve some kind of a source that sends updates in the vehicular thing, a vehicular status update, to a monitor, which might be another car. In the AR application, the source and monitor are actually the same thing. The user maybe takes an image and sends it to the cloud, and the cloud analyzes it and augments the image, sends back the augmentation as an update to the user. And we're interested in timeliness of these applications, and typically this is people understand these things in terms of update response time. So vehicular to anything applications or mission critical IoT applications require or are desired to have responses on the order of 1 millisecond. Virtual, VR, AR, and tactile feedback, people talk about 10 millisecond response times. This was discussed at some length in Misha's talk this morning. And the thing is that these things are physical. So if a car is moving 36 kilometers per hour, it's moving 1 centimeter per millisecond, and updates every millisecond tell you the position of the vehicle within a centimeter. With respect to VR, if you move your head and it takes more than 10 milliseconds to update the image, then people get queasy, and the application won't make people happy. So I got started in this field with work on sort of V2V peer-to-peer safety messaging with Sanjit Kaul about 10 years ago. And there, the emphasis was peer-to-peer, and it was just simply transmitting these messages around. Here today, we're kind of interested in kind of 2 canonical scenarios. One is each car sends updates to the cloud. These are timestamp measurements, maybe images, maybe other kinds of telemetry. And the cloud does some kind of processing. So they're kind of analogous to AR. And timestamped updates are then returned to the car. The timestamps of these updates bear the timestamps of the data that was used to generate this update for the vehicle. And our metric is the age of the most recent update. And we want this age to be small. We want updates to arrive frequently and in a timely fashion without much delay. So the 2 scenarios that this boils down to, one is the source is sending updates. This is like AR, and it is also the monitor, and it receives updates from the cloud based on its own data. And then, of course, there's scenarios where the red car is the source, and it sends data to the cloud, and ultimately the blue car, some other car is third party is the monitor and receives some of those updates. So when we talk about age, I give this talk, and many of you have seen this slide, but if you haven't, it's the kind of the takeaway message thing to remember is here. So the way these systems work is that updates go in marked by these up triangles, and I think I'm missing something here. I have like a little, where is this thing? Maybe, I don't know. I'm trying to find the little thing that gives me a little cursor on the screen, which I don't think you guys see. And I've forgotten how to do. So I guess I'll talk
But we see your mouse. We see your mouse.
You see my mouse? Like,
yes, we do. Yeah.
Okay. So I don't see my mouse in the replay. Excellent. Okay, so updates marked by these up triangles go into the network, and the down triangles mark deliveries of updates back to the user. And so the age is this process that it simply grows 1 unit of time per unit of time, because whatever the last update was, in the absence of an update, the age simply grows at unit rate. an update goes into the network here, and the age keeps growing because the update hasn't been received. And the update goes processed. And at this moment here, the update is received. And now the age drops. And the key thing here is that the age drops to this value t, which is exactly the time that has passed since this update was submitted. The age at this instant is the age of the received object, which is how long this thing has been in the system. Then the age grows and another update goes in and the age keeps growing, and then the age drops when it's received. And so these update processes and this age metric always generates this kind of sawtooth. And in this example, the update rate is kind of low. Like the age grew a lot, and when an update went in, it was processed pretty fast, and then the age dropped a lot and the age became very small. But then it grew a lot. And the issue here is that the update rate is quite low and the age gets large between the updates. On the other hand, you could say, well, let's really hammer on the system and submit a lot of updates. So here we submit a red update at time t1 and a yellow update and a blue update. Finally, the red update is processed. The age goes up. When the red update is received, the age drops to the age of that update. And then you repeat the process. But you see that when the yellow update is processed, the age doesn't drop very much. And it doesn't drop very much because the yellow update got old in the system. It was queued behind the red update. And similarly, when the blue update is received, the age is still even higher because that update was queued behind the red and the yellow updates. And so you see high update rates imply queuing delays, and that's also undesirable. So this leads one to formulate metrics where you say, let's try to keep this sawtooth process small. Let's look at the average value of the process with the knowledge that you don't want to update too fast because that causes queuing. You don't want to update too slow because then you don't get updates very often. Both of those are bad. Somewhere in the middle is good. So this prompted analysis that led to formulas for the average update age that depend on the inter-arrival time y between updates and then the corresponding system time of that update. And you get a formula for the age that depends on the arrival rate of updates, the second moment of the inter-arrival time, and this cross term between the inter-arrival time and the system time. And this thing turns out to be tricky because there's negative correlation. The longer the inter-arrival time between updates, the shorter the system time tends to be because the system empties out. So now when you analyze this for different systems, I used to show plots with many different systems, but they all look the same. They all look like this kind of smiley convex curve where at low rates, the age is bad. In fact, it blows up because in fact, you have infrequent updates. And at the other side, as the update rate approaches the capacity of the system to process these updates, you get congestion and queuing delays. And once again, the age blows up. And then for every system, somewhere down here, there's some optimal updating in the context of rates, an optimal rate, but maybe an optimal policy is what you see more generally. So this is really fundamentally different than the way people have thought about delay and latency versus rate. Historically, you analyze queuing systems or network systems, and you always get results that say delay in whatever way you measure it. Normally, typically response time or system time of an object in a network, that delay will grow in some way with the rate, and it will blow up as the rate approaches some kind of capacity of the system. When you think of a system this way, from a rate perspective, you're like, I'd like to use the highest possible rates for some tolerable delay, or I'll bound the rate in order to meet a delay objective. And with, I'm going the wrong way. Wait. With age, you get a different kind of view of the network. It says you should tune your arrival process, your offered load, in order to achieve minimum age. And that gives you a different perspective on how to build the network. So that said, age is this kind of application layer end-to-end metric. It's useful because networks are good at understanding timestamps. Age is not new. In fact, in real-time systems, there was work using age as a way to decide what a real-time system should do as old as 30 years ago. But what's happening here is that we have this emergence of low latency applications that makes age kind of be a timely end-to-end metric. And finally, age kind of suggests redesigning the network, and in this talk, redesigning how you do edge cloud scheduling and optimization. So we'll talk about some applications of that. So the first one is the simplest. The source simply submits its data to a processor in the cloud. The cloud delivers updates, and there's a service time Y associated with this round trip process. And when we started in this area, we thought, oh, the optimal thing was zero wait updating. As soon as an update goes through, you start another update. You avoid queuing, and you always keep the system busy, and you presumably operate with the greatest efficiency. So it turns out that isn't optimal. What we found out was that you can do better than that by exploiting the prior service time. So if the prior service time was y I minus 1, what you should do after you receive update I minus 1 is wait for some time. And the amount of time you should wait is some parameter beta, which is a kind of a Lagrange multiplier in an optimization problem, minus the previous service time. As long as this quantity is positive, that's what this plus is, you wait for that amount of time. The effect is you always wait for at least this parameter beta between submitting updates. And this turns out to be the optimal policy. And later I'll show you a numerical result to see what the improvement is. But the fact is numerically it's better, but it's conceptually it's a big deal because it says zero waiting updates. Just simply keeping the server busy is not optimal. And this may seem counterintuitive, but the intuition is that if the prior service time goes to 0, then the age at that instant is going to 0. And then when you submit a new update, it is a timestamp which is just epsilon above the old age. And in fact, processing that update is worthless because it doesn't reduce the age hardly at all. So what happens with this sort of lazy wait before you do something is that you avoid wasting the resources. The resources are the network resources, the cloud processing resources, and the downlink resources on updates that don't reduce the age. So you should always wait until you need an age reduction in order to send. So that was an interesting result, and it prompted more work. And you can think, well, let's do better than that. We have this kind of tightly coupled system. We have this server at our disposal. Let's consider policies that do both preemption and waiting. So when an update's delivered, perhaps you should wait, right? Perhaps that you should use that beta minimum update policy. But on the other hand, if an update is delayed, perhaps you should do preemption and restart. So here the idea is you submit an update and you're like, it's a little like when you click on a browser link and it takes too long, you find, maybe the fastest thing to do is just press the reload button. This is the equivalent of that in terms of then this service time is taking too long. Let's just restart and have a do-over with a fresh update. So this is work with Ahmed Arafa and Vince Poor that was kind of the last thing we did before the pandemic. In any case, this turns out to be a very hard problem. And and the way the system works, I'll describe how it works, is the age is, here's an update at time 0, the age is reduced. And now maybe in this interval, you wait a little bit, and then you submit the red update, and this update is getting processed, and the age grows, and and you set a threshold where you're like, okay, actually that's long enough. We're going to give up on this update. We're going to start a new update. So you preempt the update in service with a new one, and its age grows. And here we preempt this update again. I've decided we've waited long enough. And here in the third update, the purple update, well, that one, it turned out, was faster for whatever reason, and now the age drops. So this Allerton paper analyzed what is this optimal. Well, it proved a bunch of results that, oh, you should use a threshold policy, and how to find the optimal threshold. It's pretty complicated, but there's a lot of work still to be done. But here's one numeric result. So consider 4 policies. One is you don't do any cutoff, you don't do any preemption, but you use kind of the default 0 wait policy. You always keep the server busy. The next policy is actually this blue policy here. It's an optimal cutoff. You do the cutoff just right, but you also use 0 wait. You just ignore the possibility of optimized waiting. Third policy is you don't do any preemption. There's no cutoff, but you use optimal waiting instead. And then finally, you combine all of these things. And of course, combining the cutoffs and the optimal waiting gives you the best long-term average age. And the takeaway message in some sense is that this optimal cutoff without waiting, this curve here, is really the next best choice. Particularly down here at low values of a mysterious parameter C. So I haven't talked about what C is. We're basing this on a model called shifted exponential service times that actually Amina introduced me to. This service time has a constant C plus a random exponential component. And if you're a networking person, you assume this randomness of the exponential time is maybe transmission time, and you have a constant computation time. On the other hand, if you're kind of a cloud processing person, maybe you assume that C is a propagation delay or a network transmission time, and it's constant, and the randomness is in the service facility. So it's a nice model because either community can use it. But what you see in these results is that as the deterministic part gets bigger, right, that you're stuck with some long initial delay, it doesn't matter what you do, all the policies work the same. On the other hand, when the deterministic component is small compared to the random component, over here, there's very substantial differences. There's kind of a factor of about 25% improvement by optimal weighting, and maybe another 50% due to optimal preemption and cutoffs. So the improvements can be large. And if you look at kind of more generally, you have situations where you can think about multiple users, and they all offer traffic that gets buffered in the cloud. And then there's a scheduler who has to allocate resources for all of these updates, the cloud processing resources. And there's kind of a rich class of problems here involving task scheduling, like these jobs that come in. When you think about image processing, there's typically a pipeline. And in fact, an image processing job will have a number of sequential steps that different steps can be allocated to different servers. There are also opportunities for parallelism, that the scheduler can divide a job into parallel tasks, and then with parallelism, there's issues of straggler mitigation, and I think Amina has done work related to this. And of course, there's always load balancing issues that if the scheduler has information about the backlogs of tasks at the servers, it can use that information to achieve better timeliness. Another very simple application, this is kind of the most complex set of things, is that the source simply writes to the servers, and clients read from the servers. The cloud can just essentially be a data storage, right, in order to facilitate the transmission and delivery from one source to many clients. So the clients read, and the clients really desire, in a distributed systems context, they desire consistency. They want to read the latest write. And this is kind of a long-standing problem in distributed systems. If you look at the literature, there's many papers on something called the CAP theorem. The CAP theorem is in some way a folk theorem that then is been instantiated with actual models, but essentially it says you can have consistency, or you can have availability, or you can have tolerance of partitioning where the network gets separated. And you can pick two of them is the basis of the theorem, that you can't have all three. And one example of this, so systems have to do trade-offs, and one example is Amazon Dynamo, where they achieve consistency of a sort using a quorum mechanism. So the way a quorum works is that the source, the red car, writes to a quorum of size W. In this case, two of these writes are blocked, but two of them are completed, and it makes sure that at least W equals 2 of the writes are delivered. And then the client will maybe try to read from all 4 servers, but maybe it successfully reads from 3 of these servers, and so it read from R equals 3, a read quorum of size 3. And if somehow the size of the write quorum plus the size of the read quorum is larger than the number of storage nodes, then they overlap in one node, and you know that the client achieved a consistency. It read the most recent write. So the thing is, consistency seems like a good objective, but in fact, consistency is damages timeliness. You maybe spend a long time to make sure you write to enough nodes, or that you read to enough nodes. And so we looked at this from so in fact, in practice, consistency is sacrificed for faster operation. Google will talk about, an extra half-second in search delay will cut traffic. And Amazon says, an extra 100 milliseconds in latency costs them sales. And so in their systems, Google and Amazon sacrifice consistency. So we heard, you read this kind of thing in the popular press, and you say, well, let's understand this in the context of freshness, and work with my former student Jing and Amina. We had a paper that looked at this, and in fact the conclusions of Google and Amazon were correct. The age optimal quorum size, the combination of W and R that actually minimizes age of updates received at the clients, it's non-strict. You shouldn't try to strictly enforce consistency. If each one of these graphs, you fix a read quorum size, R equals 5, 1, 5, and 20, and you fix an arrival rate of new updates, and then you vary the write quorum size, and you see, for instance, there's 100 nodes in total, but with a read quorum of size 5, and for various update rates, the optimal size of the write quorum was between typically 30 and 50. So in fact, typically, many times users read data that wasn't consistent. It wasn't the latest, but but in fact, on average, that was more timely than enforcing a consistency requirement. So that said, there's many problem scenarios here. These include, questions about where are the delays? Are the delays in the uplink transmit processing, transmission? Are the delays in the cloud processing? Are the delays in the downlink transmissions? And depending on where you think the delays are in your system, you'll make different choices about how to do age optimization. Another factor to consider in formulating problems in this area is who has the knowledge to optimize. So edge users have some knowledge, but they have knowledge of when things were submitted, but they may not know the status of the cloud. Network routers may know about traffic in the network, but maybe they don't want to look at per flow state information. Cloud schedulers know a lot about the cloud, but maybe they don't know very much about the application needs of the sources. So depending on who has where the delay is and who has the state information, each one of those kind of scenarios gives you kind of a different age optimization problem. So there's kind of a rich set of problems to explore here. So I think I should stop. I'm out of time, and I'll just say if you're interested in this, we wrote a nice survey paper last year that appeared in JSAC, and it's fairly comprehensive. And there's also an AoI web page that sort of just simply catalogs all of the papers on AoI. And you can kind of, if you have an interest, you can go look at this page at Auburn University by my collaborator In Sun to see if whatever question of age you're interested in working on, who's worked on it so far. And with that, I'll stop. Thank you.